next talk is from one of our vendors who graciously helped sponsor all the goodies that you see out there and helped pay for our Friday lunch also. So LDRA, we have, let's see here, Jay Thomas. It's Jay.
Hi, guys.
And also Trevor Tidwell from United Space Alliance.
Okay, so this is, good afternoon, everybody. Today we're trying to talk a little bit about the types of techniques that we see our customers use to verify large-scale projects. And as the projects get bigger, the problems get more complex. So Trevor Tidwell's worked with us on a number of projects, and he's actually here to speak about some of the interesting problems that he's faced and how he's solved them. So in terms of agenda, I think most of these keywords are pretty clear. We're going to talk about the types of drivers that lead us to putting verification efforts up front. We'll talk a little bit about certification and then get into some key technologies. And the key technologies we're going to talk about are requirement traceability. This is making sure that you understand what you're coding to, code review, understanding your code, unit testing, ensuring your code does what it is supposed to do, understanding the test environment, understanding the model, and getting the results together. So again, we have 25 minutes, so this is a lot of topics. So if there's more questions, feel free to talk to us after the presentation. The basic driver behind all of these, and this is kind of a typical industry chart where the cost when you find a problem, the further out when you find the problem, the more expensive it's going to be. Now, this is a problem in the software industry as a whole, but in space flight and in these kinds of arenas where the failure is a loss of mission, that exponential curve gets asymptotic really quickly. And in terms of space flight in general, problems are generally catastrophic. And one of the things that I worked on a while back was I did a lot of the flight software for SpaceX and the Falcon 1 launch vehicle. Now, this is not a software failure, but this is a "Are you awake?" quiz. Does anybody see what's wrong here? Yeah, see, the fire is supposed to come from here. Not so much from here. So what happened actually was we launched out of the Marshall Islands, and there was a single nut that corroded in the salt wash out there. And that single nut caused a fuel leak, which then caused a failure. So the basic lesson here is that very small things can cause catastrophic failures in spaceflight. And the systems are complicated. And software is one of the key drivers. In fact, there's some studies that assert that half or more of mission failures, especially when you include both the vehicle and the spacecraft, are due to software failures. And that's a lot of cost. So when you look at mitigation costs, they are low compared to the cost of potential failure. In terms of mitigation, different industries have chosen different standards. We have found that DO 178B and the supplement, which is referred to as DO 178C, tends to be the guideline that most of the other standards borrow from. We find it provides really concrete guidance in terms of how you should test your code. In other industries, we see a number of other standards, but we do find that irregardless of whatever industry-specific standard you are targeting, it is important to look at DO 178B because it is the older of these standards, and many of the other standards borrow guidance from it. And let's jump into some of the key techniques that are promoted by DO 178B that we see our customers use quite successfully. The general idea here is that process is important. And this is a V diagram. This is actually a slightly technical V diagram from the DO 178B specification. And it talks about just the idea that you have to design your software first, and then you have to test it, and then you have to fly it. So yeah, and you have to do these steps in orders. And you will be surprised how many projects come to us at the very end and say, look, we have all this software, we think it works, how do we test it? In fact, making sure, the key in processes is starting as early as possible, starting in the requirements phase and making sure that all those different steps are consistent and connected. And one of the key elements in DO 178B to promote this is this idea of requirement traceability. Requirement traceability refers to understanding the connections between your requirements, your high-level requirements, your system requirements, your low-level requirements, your source code, and then in some cases your executable object code, and then your test results and artifacts. And DO 178B prescribes different levels of test and traceability for different levels of safety assurance. And these are displayed on the diagram where level D is the least safe product and level A is the most safe product. So you see in level A, you are responsible for making sure your compiler outputs its executable code correctly. Traceability management is also important. So once you have this idea of these are the connections that I'm interested in, it is also important that when you are doing your coding, you are designing, you are following your process. So deciding on a process is important, but also making sure that you are following that process by making sure your engineers have the tools to help them do the process elements. And now I'm going to pass it off to Trevor, who's going to speak about how he's worked with some of these other objectives through the last several years that we worked together.
Okay, yeah, my name's Trevor Tidwell. I've worked with Jay pretty closely using the LDRA toolset for a number of safety-critical manned spacecraft flight software projects. So he just invited me here today to kind of show a little bit about how I've used the tool set in some aspects. So a little bit about code review here. The most important aspect here is to ensure that you have a good solid set of standards to ensure that your software is meeting the expectations for its execution. MISRA, you can see here, is one of the common standards that are available. The tool set does provide a high degree of configurability, whereby you could take the MISRA, this is the motor industry standard that is fairly popular, and you can configure that, and basically you can just select the number of standards that you're truly interested in achieving. So again, you use the standards to basically identify faults and to enforce good programming practice. And again, for some of the programs I've been working on, we develop very bespoke standards models that are specific to the customer requirements for whatever application we're doing. And you mentioned here over 1,000 rules can be checked, and you mentioned you have static rules, which I guess an important thing to recognize here is that the toolset does do its operation on the actual source code, and it's evaluating the source code against the number of static rules that ensure that good programming practice. Complexity rules, a popular one here would be like your complexity. Cyclomatic complexity, what I was trying to reach there. Hallstead metrics are also some of those that are very popular for ensuring a good quality product. So talk code review. I mean, we're talking a little bit about large-scale software projects. What's important here is when you have a multi-contractor team, a multi-vendor team perhaps, you want to ensure that you have a mechanism to enforce your code's compliance across the whole team. And the tool set provides a fairly robust means to do that. You can basically configuration manage your standards model. You can provide that as part of your configuration system that all your vendors are using as they're doing their development. And one of the things that we've been able to do is to establish kind of an automation framework, if you will, to pull in these coding standards such that everyone who is actually running the standards against their code can have access to that system. So I'm going to jump ahead a little bit to the unit testing, and obviously, unit testing at the very low level, it's very key enabling technology. You know, you're breaking the pieces of the flight software into manageable parts. You know, you're basically wanting to ensure that, you know, one of the things that I've learned anyway is you want to ensure that you're kind of basically focusing on your functional unit test early on. And one of the things I've learned is that you really want to kind of defer some of your structural unit test to perhaps later in the cycle, because you do run into a lot of development churn as you're doing your unit test, such that perhaps unit tests that worked before are somehow are not going to work as well. Maybe there's some interface that has changed, so your unit test is broken. Just some definitions and some, you know, some different ways that you approach the unit test. You have the white box and the black box, which are, you know, white box, you're actually instrumenting the actual code, a little bit different than maybe G-Cov, which actually goes in and instruments the object code. LDRA actually instruments the source code. Black box, it's your kind of what it says. You're using the actual source code as part of your driver. And then gray box is kind of an intermediate method whereby you have a little more flexibility to use both the instrumented aspects of the tool set, as well as perhaps just maybe bringing in a part of the code that is not instrumented. You know, just kind of run. So constituents of the unit test would be things like a test driver. You need your set of test inputs. You can incorporate that into your test driver, or you can read it in from a file. Stubbing is an important aspect of this because it is a way that you capture a lot of your functionality. And one of the things that I've learned in doing the stubbing is that you really want to ensure that if you're going to have a regressible unit test that you can run from a vendor, you want to ensure subtle things like, you know, you want to make sure that relative pathing is important, so that you have your configuration managed system, you have perhaps a stub. In LDRA, everything is really relative to its work area, so you want to basically make sure that all your stubs have this relative path here, so that when it goes to build, it's not trying to find somebody else's path that perhaps is on another developer's workstation. Let's see, so, you know, talk a little build environment, execution environment. So portability, that's kind of one of the things I've really been involved in a lot with some of the programs that I've done. And, you know, again, the key idea here is that you want to ensure that a unit test can be executed not just at the vendor location. You want the prime to be able to bring those in and have access to all the data that they need to basically ensure that you've got some shelf life on your unit test. And so one of the things that I've learned is you really want to have a very rigid structure that you maintain in terms of a directory that you basically have in your CM system, you know, Subversion or whatever it is. You bring that out into your workstation. Because of the relative pathing, because of the CM configuration that you've established, everything is going to work for you there. Another important aspect of this to ensure the regressibility is you want to basically have some mechanism of automating how you start your tool set. And again, that because, you know, in this tool in particular, and a lot of tools, they have a lot of very configuration sensitive means in which they do their work. So I mean, LDRA is something that it is an auto code generator. It auto generates your harness. So you've got to have all that information that it uses to generate that harness. It's very important to capture that information within your configuration managed system. And so that's kind of the key idea, the last key idea there. Again, you know, the unit configuration standard is just very key. I mean, if you're going to be able to achieve the goal of having unit tests that can have some shelf life, that as you go through your development churn, as things perhaps change later on, you get some late requirements, you're not having to start over and redo the whole unit test. You basically got the system in place, you got all the data that you need to start up that unit test again. And if maybe it's just a few interfaces that have changed, maybe a stub has changed, you can go in and make that change inside the LDRA configuration file. Each test case basically has its own, it's called a test configuration file that is specific for every unit test that you do. A little bit about execution environments. I mean, you know, you have many different ways you can do a unit test. I mean, I've worked in the embedded software world, so you have different mechanisms of running the test. You have perhaps some very generic target simulations that, you know, some of the RTOS vendors like Green Hills or VxWorks provide. You also have some very high fidelity target simulations that One of the ones that does this fairly well is called Symix. I mean, they basically allow you to model your hardware to about the highest degree that you want, such that you can, when you're running your unit tests or even integrated tests, you've got the everything that you need there to model that hardware on your desktop system, be it your host system, be it Linux or Windows or something like that. So, and again, all this information here on how to build your system for running the unit test, all that is contained within your configuration managed system that is part of your release stream, if you will, so that any of the vendors or any of the prime contractor can basically have the wherewithal to recreate those unit tests. And I'll turn it back to Jay.
Sure. I wanted to talk about some of the other topics that come up quite often. And one of those is simulation environments. And this is particularly important in our world because often the processors that we're going to fly aren't always so available. And one of the things that traditionally, I actually wrote simulators in a past life. I mean, one of the things that people have perhaps focused too much is on nominal operation. And as we move forward and we understand that we have this very high risk of failure, we really need to take a higher level look at what happens when our processor fails, what happens when our peripherals fail, and make sure that we include those in our model. In fact, the DO-178C standard calls out understanding of how your simulation environment fails, and inclusion of the failure modes to be one of the key factors to basically allow you to get useful results out of your simulated systems. And another part of this is the coupling between the processors and the environment. And this is again something that Symix does a pretty good job at. There are other products that do it as well, but the idea here is that not only can they model your processor and your stuff under test, but they can also model your peripherals, your bus, and so forth. And so when you get to that level of high fidelity model, you have both system simulation and getting coverage from that system simulation environment provides a really good asset that you can link with your unit test coverage. And in fact, this is particularly important with radiation hardened processors because in many cases they're just not that available. In terms of understanding what has been tested and what hasn't been tested, dynamic analysis is key. Now, part of this is statement and branch coverage. Most people know about that. MCDC is required by some safety standards. This is the understanding that each input to your if then else changes an output. Object code coverage, making sure your compiler generates correct object code, making sure your compiler works the way it is supposed to do. And LCSAJ is a test path metric. So these are things we typically see people use. And we typically see people accumulate coverage credit with a number of means. And this is typically an iterative process where you'll start with the simulation environment, then add some host level testing, and then eventually get to the point that you're running on target. And if you're in a very highly safety critical system like a DO-178B level A system, you're also looking at the object code coverage there. Call graphs are also another way to represent this coverage. These represent whether or not, so the way our tool represents coverage is in terms of branches. And we actually treat calls from one procedure to another as a branch. And if you take a close look at that with a diagram like this, you get a really good view of whether the different elements of your system have called each other completely. And that we find is a good way to determine how well your system is tested in integration. Another important part is model-based development. Model-based development, we have typically seen walls between these different groups, the GN&C and hardware and software groups. And model-based development really allows these different groups and these different environments to share data very effectively. We talked about that earlier today. We find that the MATLAB Simulink embedded coder is becoming a more and more common environment for that. And that's something that we work with quite a bit to help people understand whether their model-based code is being adequately tested. And in terms of integration testing, we provide this full life cycle that allows you to look at your models, your simulation environment, your automatic code generation, and your test with design. So making sure that as you are moving more elements directly from the model to code, that you're still verifying the elements adequately. And one of the key elements we find there is going back to that idea of requirement traceability, tracing your requirements to the model. We find that it is often not adequate to just say that your model represents your code. You also have to have your requirements, and we find that linking those to the block level of your model is important and valuable. And to talk about this a little bit more specifically, some of the tools that we often see is MATLAB Simulink is probably what we see the most often, especially for GN and C models. We find that it does do a fairly good job of generating C and C++ code from the model. Now, and I'll get into some of the problems with this in a little bit. Rhapsody we find is a good tool for generating the structure in a C++ framework from the model. There are some executable UML standards. We have not seen them. We haven't seen them that commonly used. We typically see Simulink or Rhapsody as the driving tools. And these allow for easy transition from GNC diagrams to code. And it's easy to verify that your code, you can verify your code has been adequately tested by driving it with data from a world model. And also qualification of these code generation environments is generally available. That being said, even though it is qualifiable, and this is something as people spoke to earlier, it is generally there is generally a compliance issue in that the model-generated code typically does not conform to the standards that we typically see in our world. And this is something that people are working on. There are some variants of Simulink and Rhapsody that can generate MISRA-compliant code, but they're not that commonly used right now. So that's something, if you're using these tools, that's something you should be aware of and try to drive towards. And the other part that I mentioned as important is connecting your models to your high-level requirements. It's not adequate to say that your model conforms to your code. Does your model conform to what your software is supposed to do? And just a little bit about consolidating the results. So some of the things that we find particularly useful include system-wide traceability matrices. So these are making sure all of your code conforms to a requirement and all of your requirements conform to code. Coverage for systems as a whole, and common formats such as ASCII and Excel for exchanging data. Management user interfaces, and we do find it is often useful to be able to output a spreadsheet for your system as a whole that says, so you can present to your management and say, my system as a whole is where it is in the test and verification process. Just some conclusions to wrap up. I got a little bit of time left. So again, software process is extremely important. I don't think that we as a development community stress software process as much as we should. And some of the key elements are understanding your software components, and that's where unit test comes in, and understanding the connections between your components. Integration and system testing can help you do that. And those are some of the key enabling technologies to reduce that risk of failure. And the other part that's important here is the idea that you want to invest in this early. The sooner you find your problems, the sooner you can solve them, and the less catastrophic your problems will be. So Just a little bit of a biography. Again, and myself and Lou are both engineers at LDRA, and Trevor's been working with us at USA for quite a while. So, I guess any questions?
I don't have a microphone anymore. You guys mentioned CIMIX,
Uh-huh.
and I have quite a bit of experience with CIMIX and also with LDRA,
Mm-hmm.
cyclomatic complexity
Sure.
coverage product. And my question is, have you guys ever looked into doing an implementation of the instrumentation portion of your system on CIMIX such that the code is instrumented from the outside looking in so that what's run is not modified at all?
Sure. We've thought about that. Honestly, the reality is we haven't gotten a lot of, it hasn't been something that's been driven by the issue is that's something engineers are more interested in rather than the certifying authority. So while that is something that we've thought about doing, it's something that it's in the pipeline. It's just not that high priority right now. What we have done is there are some hooks that allow you to basically use memory rights to region. You can set up CIMIX so that regions in memory are special devices that can capture coverage from LDRA. And we find that while that's not zero intrusion, it is extremely minimal intrusion because you don't have to do a function call. You just have to do a memory write on a byte to send that data between your test environment and your simulation environment. So we find that generally solves most people's problems. So.
Yeah, that's right, because you'll get a one instruction, you'll want a one cycle output.
Exactly.
It's very minimally intrusive. I didn't even thought of that. That's a good idea.
Yeah. So we can share some technical notes on that. We do have a note on that if you're interested. So just talk to us afterwards. So any other questions?
So I was wondering if you generated any metrics out of this process that you've been applying in practice, and does it help you to manage your projects?
So in the things I've been involved in so far, we're still kind of in the thick of it. So we're not to the point of kind of doing the post-mortem on having those metrics, but I certainly anticipate coming up with that. I will say that Jay is emphasizing the earlier the better, and you really do need to make the investment up front to establish this kind of integration or kind of configuration so that you can have that system so that you can, all of your various team members, that you can evaluate what they've done, that you can rerun what they've done against your source code as it continues to change. And so again, the key idea is, in order to establish those metrics, you can't have a bunch of unit tests that somehow don't work anymore. And so that's really the key idea is capturing that information on how you run those. In LDRA's case, it's a test configuration file. And then there's an additional piece of it which initializes the tool, which establishes your structure, your file structure, your directory structure, so that when everybody pulls it out of the CM system, you get the same stuff. There's no real path dependency there that is going to cause your unit tests to break. So that's what I consider to be kind of what we've succeeded in doing. And the metrics, yes, that would maybe in a year or two.
So that was actually maybe one of the metrics I was thinking of is you imply that early in the process you had trouble reusing the unit test. And you learned to stop doing that.
Right.
You learned ways to do that. I wondered if you had, for example, graphed that to see if your improvement in unit tests able to be run had improved over time by changing your process.
They have, I just can't quantify it. I would expect that as we progress, we will be able to quantify it better because, one of the difficulties is, we are kind of in a model-driven architecture world. We do have a lot of autocode. We have a lot of inheritance, object-orientedness that does even introduce a lot more complexity into your unit test because you have perhaps something that has a number of objects that it inherits from, and you've got to basically provide the mechanism to either stub that out in some fashion, or perhaps you're bringing in some of that code so that your unit test will build. And so yeah, so you're welcome.
One question about an auto-generated code. Do you guys have a lot of familiarity with projects that have been long life projects where, let's say MATLAB, if that's the tool of choice, has been the user is upgrading to a different version and the auto-generated code is now different. Is that something you guys have run across as a challenge, or has it worked out for you?
Yeah. I could speak to that a little bit. I mean, I have run into that. You mentioned MATLAB Simulink, and that is probably one of the very commonly used autocoders out there. And yes, we did encounter some difficulties with the way that, because they come out with a new release about every 6 months, it seems, and there can be subtle differences in the way the autocode works. That ended up breaking some of our unit tests, because that code no longer matched the expected implementation in the test configuration file. I believe the exact issue was that the method was using a pointer, and then they changed that in the autocode to using a pass-by reference, I think it was. Well, I mean, that's sensitive in terms of the way things get compiled and built, so we had to go and we had to evaluate our unit tests and update those so yes, there is some sensitivity there with regard to your code generation tool. Yes.
Hey, Trevor, is there any plans put by industry to take care of that problem with having breakage due to upgrades on the product?
So what I've seen, what I've seen to help drive this, and I'm not sure if it's going to be the final solution going forward, but what I've really seen to help drive this is to drive at least some portion of your test from your model-driven environment, because then as your model changes, the hooks into your model that your environment is providing will change as well. So I've seen that as helpful. Whether that's the ultimate solution, I'm not sure. But it's something we need to.
And that is a good point. I mean, if you're doing it, and it's one of the projects I work on, we do some of the unit tests in the simulation environment. For example, MATLAB Simulink has a suite of tools where you can do your unit tests in that world. Well, in that case, the auto generation doesn't hurt you. But if your certification standard is that you must test to the actual auto generated code, and that's where LDRA really comes in, because it is testing to your auto-generated code. It is evaluating and analyzing your auto-generated code. So it doesn't know anything about models. So, that is the difficulty there with, if you can have your certification authority agree to do your unit test in the model and simulation world, then that might be the answer there.
We have seen some other spaceflight programs do that recently, so I think we're getting the hook shortly. Or
Okay.
yeah, okay. I guess we have an email address on the screen, or just talk to us afterwards. We'll be here for the next couple of days.
Thanks. Thank you.